Perfect. Hello, everyone. Thank you so much for taking the time to come to our talk series today, um, our Young Achiever Symposium. Today's speaker is Yimu Pan, who is a doctoral candidate in informatics in the College of IST at Penn State under the supervision of James Wang. His research focuses on computer vision and multimodal learning with applications in healthcare, emotion understanding, and AI assisted clinical decision making. In 2024, he worked as an applied scientist intern at Amazon, where he collaborated on projects related to last mile delivery optimization. He earned his bachelor's degree from Penn State in computer science, where he's got a summa cum laude, and in mathematics and statistics with magna cum laude. And in his free time, Yimu loves to watch. So I hand it over to Yimu.
Thank you. Thank you for the introduction. It's great to be here, and thank you for all your time to have this discussion today. So, what I'm going to talk about is the cross-modal learning and foundation model in medical AI, mostly related to my thesis topic. And I will cover some techniques, popular techniques, and the techniques that I used throughout my PhD, and also the applications in placenta analysis. So let's get started. First of all, the outline of the whole talk is about the first part, cross-modal learning and the foundational models. And you can think of them as a toolkit that I will be used to build the rest part of the solutions. The rest of the part of the talk is about problems and solutions in automatic placenta analysis and medical AI in general. So let's get started to page. So in medical image, unlike the not traditional, but unlike natural images, we are facing specific problems. And those problems are, and also the medical images have distinct characteristics compared to traditional natural images. So those are, medical images are usually accompanied with a report. And they are usually biased because when you collect data, they are usually either from a few sites or use a few machines to collect the data. Due to the bias issue, they don't usually share the data across different hospital sites. And also because of the equipment you are using, you usually have, and the expert you require to get the data, you usually have limited quantity. And the tasks we are doing for medical image are like lesion classification, organ lesion segmentation. So now it brings us to the research topics that we are interested in medical image. Is first of all, domain generalization. If you train using data from one side, one hospital, how can you generalize to different hospitals? And secondly, we want to overcome the data scarcity problem. We don't have enough data. How can we get a good performing model? And then we also want an efficient inference, because if you want to use the AI, like you want to scale the application of medical tools, but if your model require like a high-end GPU to run, they are not even scaling it. But like not a lot of people can afford that. So that brings us to those topics. First, let's introduce some techniques. You can think of it as a toolbox, and this might be interesting to you also as a background as this kind of topic. This is very popular work, and it's probably a foundation for many of the current vision language model. So it's called contrastive learning, contrastive language image pre-training. So what it does is quite simple. First of all, they collect a very large data set. What they do is they basically query Google or whatever search engine you want, search for the image, and the image on the social media or the post, the whatever website you're using, they usually have a text description describing what the image is. And once they collect the both pair data set for both the image and the text, they now have actually a weakly labeled data set. And what they do is they use a method called contrastive learning. Basically, if the text matches the image, we make sure their embedding space are similar. And if the text doesn't match the image, for example, if you show me a cat and you are saying this is a dog, I push their embedding space away. And what that will bring us is a very good embedding space that we can later use for classification. And what is shown here on the right is actually a image classification. And you can predefine, for example, the plane, car, dogs, those classes, and then just compare the similarity in the embedding space to the image. You can have a classifier easily. And in the medical area, there are similar work. It's a little different because this work is actually, if I remember correctly, it first came out before CLIP. And what it does is, if you have a medical report, you can encoder use a text encoder, and then you can encode the image, use an image encoder, and then you can do the same thing in the embedding space. The only difference between this and CLIP is this use a frozen text encoder. Basically, you pre-train the text encoder first, and then do the contrastive learning to train only the image encoder. And people quickly realize that there are some problems with the simple contrastive learning, is that you are giving away local information. For example, once you have the text encoder encoded, you have one vector. You have the image encoded, you have one vector. What if they are different part of the report that's not associated to the same part of the image, right? Now, people have proposed we can just simply use local level contrastive learning. We take this patch of this image, this part of that text, and do the contrastive learning. Then they show that actually can improve the performance. Later, people also realize that, like, if we fix the text encoder, or if we just unlock the text encoder and continue training both, there is a problem where your model tends to find shortcuts. And once it learns how to separate the two things, it would just ignore the rest of the text. So people has come up ways to keep the text encoder performance without the basically the model finding shortcut, is use a masked language modeling as in the BERT training. What you will do is you would mask out some part of the text and also ask the text model to predict the mask token, and that will help the model make sure it doesn't collapse that easily. And for medical image, we also have some additional information that we can use. For example, we have additional knowledge of what each of the terms should look like on the image. So if you just have additional knowledge additional knowledge from, for example, a knowledge graph or things alike, you add that to the contrastive learning or use that to guide the contrastive learning loss, you can further improve the performance. So that concludes like the basic ideas of the contrastive learning and how its application and evolution in the medical image domain. Now let's go to another technique called the diffusion model. This is usually used because we have data scarcity problems. So this is usually used to generate synthetic data to expand your data set. Let's give a little introduction on what diffusion model is. Put it like the simplest way is, once you have an image, you add noise, you train a model to denoise that image. The model learns the distribution of the data set. And if your model is, if you keep applying the same denoiser from the random noise until it gets a real image, then because the model learns to denoise, so it's able to reverse the noising process and to get the clean image. So I'm not going to go to detail of how this is done. The most popular work is actually latent diffusion model. The only difference is the denoising happens in the latent space. You first train a variational autoencoder. Autoencoder is just you take the input image, encode it into a latent space, usually smaller in a spatial dimension, and you project it back to the pixel space. And that label is just your input. So that's why it's called autoencoder. And once you have the autoencoder, you in the latent space of the autoencoder with smaller spatial dimension, you just do adding noise, denoise. So so that you can generate the image. And here you actually want a text condition here, so that you can condition your noise on the text. So later, once you generate the image actually follows your condition. For example, if you tell the model to generate an image of a dog, if you give a condition like a shape of a dog or just text description of the dog, you can get that conditioned image. And the reason they do this is for efficiency. Traditionally, if you add noise in the image space, if you have a very high resolution image, it's very difficult. Both in the training and in the inference time, because you need to apply the noise multiple steps. And here, once you do it in the latent space, you are actually reduce the computation resource by like a large amount. And this is used everywhere nowadays. Now, we already have conditional generation. However, we cannot have fine-grained control. For example, now I want a dog, but I want a dog of different size, different shape, different appearance. That's like, it's still difficult for you to describe in the text description. A follow-up work to solve this problem is called control net. What this is not a new model. This is just a little control module add on top of the original latent diffusion model or stable diffusion. What it does is it encodes your control, either a sketch, depth map, or edge or post. You encode those control and add that as part of the diffusion process. And once you do that, your image will actually follow very closely to your input control, as in the first row. And the next few rows are the generated image. And if you take a look at this, we already have a dataset generator. So if you want to classify, let's say, different kind of shoe, you can just give the use your unlabeled dataset or whatever, and use the edge map to create more more variance in the dataset. And if you, for example, you're doing a segmentation, if you just apply your segmentation mask here, and you can generate a lot of like images with the same class distribution or same semantic distribution. In the medical image field, it's actually widely applied. First of all, as I said, you can use the model to generate images. This method basically based on some domain information about the medical image. They normalize the color before tuning and generating new images. And they show that improve the performance. Later, people actually found, because the generated image can give you some error, if you have an iterative pipeline to refine your generative method, and then you filter out some incorrect images, and then do that again, keep doing that, you will get an even better result. And that actually conclude the diffusion model in the medical image application. And there are more work on that, but they basically propose some module based on domain information. Overall structure follows the stable diffusion or control net structure. The final step is another very popular line of work called the segment anything model. What it does is you have a image and you have a user to click. Sorry, somebody said something? Okay, so you have a user to click the image or draw a bounding box on the image, telling the model which part of the image you want to segment. And then you also have a complete label. For example, if you are talking about the scissor, if you just click on the scissor, I have a few options of what I want to segment. And those are the information to fit into the model. And the model will learn based on the user prompt to produce a corresponding segmentation mask. And you can also call it interactive segmentation model. In the medical domain, actually people tend, because that model can it's class agnostic, so you can actually train it using a very large data set. And SAM is trained on a very large data set. I forget how large of the data set is, but it's like order of magnitude larger than normal segmentation data set. And here, what people have done is because the SAM is already very good, so they try to adapt the SAM to the medical field. What they do is they use the medical image data set and generate the bounding box around the ground truth segmentation mask, and using that bounding box as the prompt, and then fine-tune SAM on medical image data sets to produce better results for medical images. And that model, again, is interactive. I think another line of work is to adapt SAM automatically, because sometimes if you use the model downstream, you cannot assume the user has the medical knowledge to draw the bounding box. So what you do is you train on the label instead of the bounding box, and just use the SAM as a feature encoder, so that your feature is basically cleaner and you can have a better model. Use SAM as a pre-trained weight. This is fully automatic. There's no interactive ability. You cannot click anymore. It just does that automatically. So that's the segmentation part. Now, with those ready, we can talk about the problems and solutions in the automatic placenta analysis and also in broader medical AI. First of all, let's introduce placenta a little bit. It's just a temporary organ that forms during pregnancy. However, it actually acts as a fetal life support prior to delivery. It helps you understand the health of both the baby and mom, actually. But it's very useful. It's rarely studied. Only 20% of placenta even get examined by the pathology, which is to find all the kind of lesion diagnosis from the placenta. And the pathological exam is current gold standard. And what they do is you have a placenta, and it gets sent to the growth room, and when it's all trimmed out and pictures are taken, and they figure the placenta, part of the placenta that likely has the problem, they would produce microscopic slides on that part. And then a pathologist will manually examine the slides to create a path report, which is shown on the right side of the slide. And the limitation here is this takes a long time. As you see, there's already 3 stages involved in the process. And you have to have a hospital level equipment to produce the slides, to actually have a microscope to look at the slides. And you also have to have an expert, a pathologist, which is very rare, actually. So the solution is to do it automatically. Like, let's use the AI tool we just described. Can we do that, right? So previously, people have done that. This is from our lab. This work is just use supervised learning, pre-trained on ImageNet, and like, let's say if we have hundreds of annotations, and can we do a model that does the automatic analysis of some pathological terms and some morphological terms? And they found the deep learning is able to do that and do that very accurately. However, that brings us to our challenges. If you train only on one hospital, you need to generalize your model to other hospitals. But usually that's not gonna work. And also, your sample, you don't have enough data to train a very good model to begin with, because you need to collect data that every step involve a human or a few people in the loop, and they are experts. Additionally, like, the likelihood of finding some potential errors or symptoms in the placenta.
It was not alone.
Anything? Okay. So the class is the distribution is very imbalanced. You have very long-tailed problems, so that the model will be trained inefficiently. And we have path report. A lot of medical images has report. But if you just simply doing supervised learning, those information in the report, for example, the correlation between the stuff in the report are not modeled. So we want to do that, all of those at once. So the aim is to first improve robustness against domain shift so that your model can work on different hospital, different setting in the application. And also we have multimodal data, use that. And we want to use the pre-trained model just to improve the performance, because in deep learning, usually if you have a better pre-trained model, your downstream performance will be better. So now let's go to the work. This is, from here, it's going to be something done by me, either me or my lab mates. Let's take a look at the overall pipeline, what we want to do. What we want to do is from the input, we can have like all kinds of images of the placenta. And we want to get a segmentation. And the user can actually modify the segmentation if needed, right? If it's correct, then good. If not, we want to modify it a little bit. And the segmentation can give us some morphological characterization, for example, the size of the placenta, the circumference, and also we can probably predict the insertion point. Those are related to the specific things that the placenta researchers are interested in, and also related to some diagnosis that the clinicians can make based on for the patient, and also the diagnosis, which are directly related to the pathological terms, and that will be related to classification problem. So it all boils down to segmented segmentation and classification. First, let's talk about the morphological characterization of the placenta. As discussed previous slides, we want to get the segmentation. We want to get the size, shape, all the kind of length and width stuff. So to do that, we need to use the model trained on one side, but we want the model to generalize to different sites. So the goal here is to improve robustness. We're going to talk about in general how, because we already distilled the problem into a robust semantic segmentation problem. So we're going to demonstrate as a medical AI tool instead of just placenta. So we don't have assumption on the downstream domain. We don't know what kind of image condition we will be using. And if that's the case, we can think of how we can train using our already existing in-domain data set and to improve the model performance. So first assumption we make is the model doesn't generalize because there is some noise that's only related to your training data set. And it does not present in, it's not present in the downstream target data set, which you don't know. So if we can reduce that noise, we can get a more robust model. If you know photography, in photography, there is a method called the image stacking. Basically, if you take the image multiple times, you take a lot of images of the same exact thing, and then you average over them, you will get a cleaner image. If we can do that in the pixel space, we can also do that in the latent space. If we have the same image of the same medical whatever, they correspond to the exact same semantic feature or semantic segmentation mask to make it simple. Then if you average over the feature, they are cleaner feature. If you train your model against that feature instead of the original feature, you get a better model, a more robust model. However, how do we get a lot of images from the same semantic segmentation mask? Remember control net. If we just apply control net here, we use our training data set. We don't need any extra data set, data. We just use the training data set. We apply the control, the segmentation mask as the control. Then we generate a bunch of new images, train and generate fine-tune control net and generate a bunch of new images. If you look at the images generated for all the data sets, the bottom 3 rows, they are pretty good already. And however, they do have a lot of variations in terms of both the semantic representation and the color change, and also the change of the different noise. You can tell they are from different distribution. And this actually gives us a good set of images to estimate a good semantic feature in the latent space. And if we have that, what we need to do is just to train against the average feature, use each image. But that will require, to get the average, you will, for example, if you want an image to get the average, you need to do n inference at each training iteration, which is impossible because if you're training, like your training time is 1 hour, now it's n hours, right? And you need a large n to get a good estimation of the mean. But luckily, we have a thing called Bayesian updating. What it basically tells you is you don't have to get all the sample at once. You can get it one by one and update your prior, posterior, and keep going, and eventually will converge to the true mean. So now you just need to apply that to the distance function between any sample to the mean sample. And what you will get is that is actually upper bounded by the distance between any two samples. So you don't need to worry about the detail, but the message here is you only need 2 samples in the training set at each training iteration. And the modification after you generate the stack of images, the modification from traditional segmentation model to this method is just add a similarity loss between the 2 images of the same semantic segmentation mask. And that's all you need to add. And you generally get a quite decent performance improvements for across data sets. Now let's go into what you can do additionally to have the user to correct the segmentation mask. This stage, what you want to do is, let's say at your application site, once the user takes the image, if the image has a little error, but the user knows there's an error, what would you do? The user can either use the brush tool to paint that part out, or we can use the interactive segmentation tools for the user so that the user only need to click a few points to correct the segmentation mask. However, previously, if you remember what we have discussed before, there are methods to do automatic segmentation. There are methods to do interactive segmentation, but there is no method to do both. So what we try to do is to have one model that not only automatically generates segmentation mask, but also accept additional user prompt to get a better result. We call it automatic and interactive segmentation model. And the core for this model is just a AI prompt, automatic and interactive prompter. What it does is, based on the image, it's automatically learn the prompt associated with each mask. Here we use a point prompt. The prompt, and then if the prompt is associated with the mask already in the during the application, when the user want to use the model, the user only need to click the points instead of having to use the brush tool to correct the mask. And the model is, you don't need to worry about the detail. The thing here is the model takes in the model takes in the point query, basically encode each semantic information of each class, for example, cat, dog stuff. And then it will extract points from the image based on the query. For example, if it's a query for dog, it's going to extract some points from the dog part of the image. If it's a query for cat, it's going to extract some part of the points from the cat. And then what it will do is this point extracted will be, instead of using just a one hard point, I'm going to use a generalized point, which is a distribution of the probabilistic distribution of where the point could be. And once we have that, all is left is to train the model to generate those points. Here, we don't have ground truth location of the points. We only know it's going to be inside the segmentation mask, but we don't know exactly where it should be. And so we have to have the model learn it by itself. First of all, we have few laws to encourage that. We want the points to be correct. Basically, they should be inside the segmentation mask. And we want the point to close to 1 hot, because when the user actually use the model, you can't ask the user to click a probabilistic map over all the pixels. You just want a 1 point. So if the model already knows how 1 point should look like, it's better for the user to use the model, or easier for the user to use the model. Then we want the point to be diverse, because if every point goes to the exact same location, you might as well just generate 1 point. So to generate more points, we want more diverse points. Then if you do that, what the final model can do is, if you apply it automatically is performing on par with all the existing method, and it's also comparable to other SAM-MED, which is another automatic adaptation of segment anything model. So basically that says you can use this to replace your automatic adaptation model for SAM. In addition, if you add a few of your prompt to the model, you get a better performance. That basically says this model, in addition to its good automatic performance, can also accept additional user prompt to get a better result. And people might say, why can't you just use SAM? If that's the case, you have to use interactive. You have to do the interactivity anyway. The problem is if you just use SAM, SAM is not adapted for medical image, and it's gonna give you some error, especially when two classes the features are very similar. For example, if you look at the fourth row in the interactive section, if you look at the ACDC performance, the dice performance for some of the class, for example, MYO, is very low, because that class gets confused with RV quite often. And even if you adapt it using interactive method, for example, like MathSam, because MathSam use only bounding box instead of points, there are some issues with bounding box. And for interactive adaptation, it's very difficult to use points. So the confusion is still there. If you look at the MYO class, it's still terrible. Only if you, for example, use point prompt and to use the automatic and interactive segmentation method, then you can get the performance back to the good to the good numbers. So that concludes the segmentation part of the model. Now we actually have the user intervention in the segmentation part. What's next is to perform the diagnosis. Again, let's revisit what we have. We have an image, and we have the path report as training data. So the easiest way is to do a vision language contrastive learning, as we have suggested in the previous two toolkits. What you do here is you input the image, input the medical report or path report, and you do contrastive learning. But here we propose something also to reduce your model might collapse because of it only needs one dominant feature to distinguish between positive and negative pairs. So to remove that effect or to reduce that effect, what we do is first let's do a distant function that relies less on the dominant feature. From the graph, it's obvious we choose the one with the lowest reliance on the dominant feature, which is log cosine h. Once you have that, another thing we can do is, remember there's a thing called dropout. If you apply dropout, your model is more robust. Here we don't apply dropout, or we don't apply dropout. Instead, we just apply a random mask over the feature space, so that every time we only compare a subset of the feature space. In that case, we do something similar to the dropout. Well, but this is in the feature space, so our feature space is more. The feature space is more robust instead of the model being more robust. If we apply that compared to the traditional convert, which just do contrastive learning, our method can improve the performance quite a lot over all the tasks we are interested in. Additionally, we have a few problems here. The report can be in various variable lengths. So sometimes you have a longer report, sometimes you have a shorter report. But you need to encode the text everything at once. And also you don't want the model to forget like part of the text to encode in order to minimize the loss. And second, if you encode the text in a different order, because in your text encoder, usually a transformer, it has a positional encoding. The order of the text actually matters. So we don't want that to affect the performance. The solution is we need a dense and order agnostic way to represent the text feature. To do that, what we do is we simply split all the text by terms, and then we encode each of them separately. And later we recompose them into a probabilistic distribution. And we train our image against that distribution instead of a simple vector. And what that will do is that will bring the robustness and also the performance. Here is to show why that's more robust to use the distribution feature instead of just a simple point estimate. If you look at the V1 on the far left, let's start with this space. You have a bunch of vectors, and each vector can represent one text feature. And if you just change one feature a little bit to V2, you make one feature shorter. If you look at the point estimate, which is the orange arrow, the arrow changes quite a lot, but the distribution doesn't change as much. If you look at the V3, you actually have a large change of the feature, the vectors, as shown in the dark vectors. That's a lot more change compared to V2. But if you look at the orange vector, it doesn't change as much compared to V1, even if like the individual feature changes drastically. But if you look at the distribution actually changes a lot. So if you use the distribution to represent the feature space, it's giving you more robust feature. And using this method, we get additional performance improvements over the previous method we proposed. Now we are facing the additional problems. We are using a frozen text encoder, which there can be a domain gap between the text you train the encoder and the text of the placenta pathology report. Also, we are not aligning local parts of the report to the image. So that can also bring some performance improvement. And here, we try to incorporate all of those to the model. What we propose to do is, first of all, we have more data here. And then what we do is we first use a better pre-trained the clip weights to initialize our model. Second, we use a BERT encoder to encode the text feature. And now we have two text features. One text feature is used to update along with the image. And another feature is just to keep the model from collapsing into a trivial solution. Because again, the model can find shortcuts to get the dominant feature. And once we do that, we now use the text feature to query the patch-wise image feature so that we have local information. And with the local information, the distillation part, and also the pre-trained weights, we do contrastive learning altogether. Next, we need to evaluate the robustness as we discussed. We want the model to perform well on different settings. So we need to evaluate that. How we evaluate that is we use a program to generate a bunch of those artifacts that mimic what people will see in the real world application, like blood, glare, JPEG compression if you use, depend on your device, and also shadows if for example, your light source is behind you. And also if you shake your hand, you can get a motion blur if your camera doesn't zoom in pretty well, or if you are zooming while taking a picture, you get zoom blur or defocus blur. And also the exposure can change depending on the lighting. So we have also brightness, contrast, and also saturation. Additionally, your light source might cause a difference in the white balance. So we also model that. And those are all here to evaluate how model performance under the different situation. We call it robustness evaluation. So here we have two types of evaluation. First, performance. Second is the robustness, which is the thing we proposed. And performance just evaluate on the original image. And if you look at the different module, P is just a clip width. We can ignore that because we use that throughout. D is the distillation part. Basically, we keep a fixed bird model as part of the training. And R is the retrieval, or we can call it the local level information. If you see from the orange boxes, using the local level information improves the model robustness. So the model will be more robust if you apply it to a downstream different settings, different applications size. That module will help the performance there. And the distillation from a frozen bird will improve the performance, as the bird might have some knowledge related to the medical information that is outside of the capability of a past report, which can improve the performance. If you look at our latest model, which is this model, compared to the two previous model we have, this performance improvement is significantly larger and mainly contribute to patient weight, the distillation, and also the local information. And if you compare to other even better method, better like a pre-trained weight, like a EVA clip, if you should just apply EVA clip naively, the performance is not very good. It's actually on par with our previous recomposition technique. So that further highlights how important the local information and the external knowledge of the medical information can contribute to the model performance. So finally, in summary, we discussed the entire pipeline of what we want to do, and each component are summarized as in the previous slides. So the result is a robust, generalizable, and efficient framework. As one model, we just need to train one encoder, and we can perform all kinds of tasks. And along the way, we also have techniques that will improve the robustness and the usability of medical AI in general. So the next step actually is funded by CSR AI. It's a triage tool, which is used, for example, once I have a placenta, I just need our tool to take an image, and the tool will guide the clinicians and tell the clinician whether this placenta should be sent to a full path report, because path report takes a lot of resource and a lot of time. Hopefully, this will better use the resource and for the full path report evaluation. And also, we want to perform evaluation on multiple sites just to see the performance. And we thank all the fund agents and all the collaborators from different institutions to make the project possible. Any questions? Either of you go. You can go. Yeah, you can go. Yeah, I'm not sure where the mic is actually.
This is going to sound a little bit off the wall, but those of you who know me should expect as such. I'm thinking about almost the placenta as an analog to a holographic boundary from the principle of the holographic principle of physics and information theory. And I'm wondering if there's not an analog between this and some of the work that both Marcus Buehler at MIT and Chris Fields of the Active Inference Institute is doing in terms of their work. Have you considered, I mean, I'm zooming out from just the problem of the placenta here.
Mhm.
I'm really looking at it more from a systems boundary, and really the placenta as a systems boundary is what and as a temporary system boundary is what kind of drew my mind to this point. I guess my question is this generalizable? That's the question. Thank you.
Generalizable to
Other domains that might be outside of just medical imaging.
it's actually like the other way around. It's developed for any images, and it can be applied to medical image. So in a sense, it's generalizable to medical image.
I guess I'm speaking more about the UI work that you did,
But-
making it more simple for the labeling for selectors. Yeah.
Oh, so you mean the triage tool?
Yeah.
That is a next step. So we don't have that yet.
Okay. Perfect.
User interface is what you're asking?
Yeah.
Yeah, the user interface where we're.
Oh, you got clicking thing, right? Oh, ASM is generalizable. ASM can be also if you this website. This is a GitHub link. I also did other work like a shadow detection and all other kind of camouflage segmentation, something like that. It doesn't matter what image you use because yeah, as long as you have the data set to train the model, it should all work well.
Yeah. Sorry for
No, that's good. Thanks for the question.
So regarding the first part of the talk where you explored like generating training data sets using diffusion models. So have you explored the problem of memorization in diffusion models? Because diffusion models are typically known to pick samples near the mean most of the time. So if you train a diffusion model and use that to generate the training data set, you will get most of the data set that you will get will be near the mean of the distribution. So have you explored the memorization issue?
No, we have not. However, it's actually a good question. Well, I'm aware of the issue. It's just in our application, for example, in this setting where I want to generate multiple images for the data set and I want to use that to estimate the mean, even if it's around the mean, right? I just want the mean. Yeah. So that in that sense, it doesn't matter. And also it has a little variation, and those variation are, I would say, good enough for the application. So that issue doesn't really cause much of the problem here in our application. Yeah.
To ask about the semantic stacking work.
Mhm.
So you said you're doing the averaging in the latent space.
Yep.
Why?
Because if you are doing semantic segmentation, averaging the pixel space, you get a noisy image, which
Like masks with this stuff.
you wouldn't know. Averaging the pixel space, you wouldn't get a real image anymore. It will not work anymore.
I guess I have to read the paper, but like why the Bayesian update is.
Oh yeah. So basically that's just to reduce if you want the average, right, you need to compute the latent space feature before you can do the average for each image. If you have 16 image, you need to compute it 16 times at each iteration. And because your encoder is updated at each iteration, so you need to recompute that every single time. So to not recompute that every single time, you use spatial updating so that you only need to compute it twice at each iteration. Yeah. Another question? Oh, yeah, sure. Let me see if there's any questions on Zoom. I don't see any either.
Well, thank you so much for coming, everyone. please feel free to grab some snacks on your way out, or if you have any more questions, Yimu is here for a few more minutes.